I just want to help you guys get ready for your quiz tomorrow. I'm going to show you a couple of examples on how to solve some dimensional analysis questions. You'll need your reference table, and you'll need the table with units on it in case you need to memorize some things. But we'll start with number one. It says, show that joules are a unit for the variable expression, mass times distance squared over time squared. So I know that joules are a unit for energy and for work. And for work, there's one basic equation, but for energy, there are several. One of the ones that I know will be useful here is a unit, or is an equation for kinetic energy. And it says that kinetic energy is 1/2 mv squared. And the reason why I have an instinct that that one's going to be helpful is the quantities, mass and velocity squared. So I know that velocity is distance over time, and I see distance over time in the original question, and both of the quantities are squared, just like it would be here in the v squared. And then mass, of course, is mass. So it's pretty much solved at this point, ignoring the 1/2 because it doesn't affect the unit. M obviously is mass, and v could be thought of as d over t. And both of those quantities are squared, so you get md squared over t squared, which was the question, so that is solved. Another example is in number 2. It says, show that newtons per kilograms is equivalent to meters per second squared. So newtons per kilograms, I'm recognizing that the unit newton is actually the unit for the quantity force. So instead of newton, I'm going to think of force. And kilogram, I know, is a unit for mass. And when I see force over mass like this, I'm actually already thinking that these are standing in for acceleration. And acceleration, I memorized, is measured in meters per second squared. For those of you who haven't memorized it, you can derive the unit for acceleration like this. Acceleration is equal to a change in speed over time, and speed is measured as distance over time. So distance over time is going to give me distance over time squared. And distance over time squared would be measured in the units, meters over seconds squared. So that's how you can derive the unit for acceleration if you don't have it memorized. I'm going to skip number 3, but because it's not a math question, but in number 4 it says, show that v squared over d has the same units as acceleration. So this is sort of related to what I was just showing. Velocity is distance over time. So when I see velocity squared, I'm thinking it's actually distance over time. Now it is squared, so let me square both. And it's actually set over the quantity distance. So distance squared over time squared over distance. What you can do is you can think of these two denominators as being combined. If you do d over t over d, then you can take the t squared and the d and you can put them both in the denominator of a single fraction. So I'm going to get d squared, which was just what was on the top, and I'm going to leave it there. But I'm going to put it over the d that was already there, and the t squared, which I'm bringing down to sort of simplify this fraction. Now, basic algebra tells me that this d is going to cancel one of the d's in the numerator. So I'm going to take out the square, and I'll just leave 1, and then I have d over t squared. And the quantity distance, of course, the unit for that is meters, and the quantity time, the unit for that is seconds, so seconds squared, and that is the same unit for acceleration, which we were just speaking about. I'll see if there are any more down here that are worth it. Okay, here in number 8, I'm seeing some promise. It says weight is Fg, or force due to gravity. Find this on your reference table for future reference, and show that a possible unit for weight is kilogram meter per second squared. Okay, so Fg is force due to gravity, and we just want to show that a possible unit for it is kilogram meter per second squared. So normally, forces, I would just say, are measured in newtons. But Newton, standing in for force, Newton is a derived unit. And that means that it's made of other units, and some of those units are fundamental. And what looks like what they're doing here is they're giving me the unit for force, but it's going to be in fundamental units. So I'm just going to start with the equation for Fg, and I'll just find the fundamental units from there. So Fg is a lot like other forces, but we write its equation just a little bit different. Instead of writing F equals ma, we think of it just a little bit differently. We say that F equals mg. So Fg equals mg. So it's really similar to F equals ma, but a little bit different because instead of having an a, we have a g. And just for the record, this little g, that is an acceleration. It is a, but it's a very special kind of acceleration. It's the kind of acceleration that we have here on Earth when objects are in free fall. We'll study that a lot this year. So this equation is F equals ma, but it's just being really specific about what kind of acceleration it is, and it's the free fall kind. So I'm going to plug in units just like I always do. The unit for mass is kilogram. And g is a kind of acceleration, and therefore its unit is meter per second squared. Therefore, I am already seeing that I've arrived at the answer, kilogram times meter per second squared. It's all right here. It's the same thing, kilogram times meter per second squared. So all set there. And then at number 10, let's see if that's worth it. Yes, I can see that it is a dimensional analysis question. It's asking me to show that an acceptable unit for impulse is kilograms times meters per second. My suggestion for this is to look up on your reference table the equation that involves impulse, and you'll see J equals F net times time equals change in P. Now, there's sort of two ways to go in this one. One of them is going to end up being the wrong way, and the other one's going to end up being the quote-unquote right way. So I'll start with the wrong way, because I'm going to try to show that J is equal to, kilograms meters per second. I'm going to start out with F net times T, though, which is the actual equation for impulse, and that's going to give me newtons per seconds. Newtons per seconds is not the same thing as kilograms times meters per second. So I'm actually going to keep going, and I'm going to put in the equation for delta P, which is momentum. And if you look on your reference table, it's going to be nearby the equation for impulse. There's an equation for momentum, and its equation is P equals mv, or mass times velocity. I'm going to use this part of it. I think that'll be the key to the question, to getting it right. So m is kilograms, and v is meters per second. So what I've just shown is that mv, or mass times velocity, would be measured in kilograms meters per second. And this unit also would be appropriate if you follow the equal signs back. It would be appropriate for expressing J. So I'm saying that J is equal to kilograms meters per second. And that is actually solving the question, because that's what they asked me to do, show that an acceptable unit for impulse, J, is kilograms meters per second. And there it is. All right, so that's my little review of dimensional analysis. Please study. You will have a quiz on Monday. Also, do a lecture over the weekend. The lecture that you're supposed to be doing, I believe, is 1.2. So do Cornell notes for that, and I'll see you on Monday.